So this lesson we're going to work on the derivatives of the remaining trig functions. Before I get to tan, cosine, cosecant, secant, and cotangent, I just want to review what we learned last lesson. And I won't go through every single nitty-gritty detail because obviously you have a video for that. But hopefully you know that if y prime is no, let's not do it like that. Let's write it this way. This is a better notation. The derivative of sine. This is way better. The derivative of sine we've discovered is cosine. And we've also discovered that the derivative of cosine is actually negative sine. Now, one thing that I didn't do in our last lesson that I realize right now that I could do is just do a quick graph of sine to cosine and just be able to see how really they are similar. Right, like right here, you've got a positive slope in your sine graph, but then you get to the point where you have a slope of 0. And then right here, you'd have a slope of 0, and right here, you'd have a slope of 0, right? All of those maximums or minimums, you'd have a slope of 0. Here, you'd have negative slope, and then here, you'd have positive slope, and then negative and positive. And so you can kind of see how sine and cosine are related. And that same thing would work with cosine back to sine. So anyways, that's not really the point of today. Today's point is I want to show you the remaining 4 trig functions, and then we're going to use those rules in a couple more examples. So it's a pretty brief set of notes. This shouldn't take overly long, but I do want to show you where these proofs came from. So we're going to find the derivative of tan. And to find the derivative of tan, we're going to recognize that tan is equal to sine over cosine. So I'm really asking you to find the derivative of sine x over cosine x. And this is essentially, it's a quotient rule, right? And one of the points I tried to make in the last lesson, and I want to make them going forward, is that, I mean, even when we use trigonometry and exponents and logarithms, we still need to be able to use our power rule, our quotient rule, our product rule, our chain rule, right? All of those still apply, right? So we need to use our quotient rule, which goes like the following. It's the bottom times the derivative of the top minus the top times the derivative of the bottom. And all of that is divided by the denominator squared. So we have 2 derivatives left to take. We've got the derivative of sine right here, and sine derives to cosine. And then we have cosine right here, and cosine derives to negative sine. So the last thing we want to do is clean this up a little bit, because every single time that we write out tan's derivative, we don't want to write this mess. This is a bit much. So hopefully you can see that these first 2 things right here, that'll give you cosine squared x. And then a couple of double negatives will make it positive. That'll give you sine squared x. And then one more step after that, if you're familiar with your identities, and maybe now's a good time to point out that your trigonometric identities, this is my personal opinion. In 30-1, I think they're very not purposeful. I really don't believe that that actually belongs in Math 30-1 because we don't use them for anything there. We just teach you that there's all these rules of how you can replace certain things with other certain things, and we kind of show you that, and it's kind of a little bit of a game. And there's some tricks that we can show you to get around diploma questions, but it's not very purposeful. But I promise you right now you can see how this is purposeful. If you understand how these identities work, you'll know that cosine squared and sine squared, they actually are an identity that gets you to 1. And then 1 over cosine is known as a secant. And so if you have 1 over cosine times 1 over cosine, really what you have is a secant times by another secant, which is why you get secant squared. I don't know that I really need to write out this little step here. This from here to here is hopefully pretty logical. But this adds our 3rd rule now. So sine derives to cosine, cosine derives to negative sine, and tan derives to a secant squared. So there's our 3rd one. Well, let's keep going. Let's differentiate the cotan graph. Well, again, with your knowledge of identities, you'll know that cotan is just the opposite. This is not opposite, but the reciprocal. This is cosine of x over sine of x. All right, so again, let's use a quotient rule. We'll do the bottom times the derivative of the top plus, no, not plus. That's not the product rule or quotient rule. Okay, take one more time. The bottom times the derivative of the top plus... Oh my goodness, I did it again. Whew. All right, one more time. Let's not get this wrong. Minus the top times the derivative of the bottom. All over the bottom squared. Okay, so again, we know the derivatives for cosine and sine. Let's just plug them in. Sine will stay there. Derivative of cosine will be negative sine. And then cosine. Derivative of sine is now cosine. And this is all over sine squared. So what we're left with this time is negative sine squared x. Also subtract cosine squared x, and that's all over sine squared x. And at this point, again, we've found our derivative. I mean, really, we actually found it up in this step up here. But we need to clean this up a little bit because every time that we try to find the derivative of a cotan, we're not going to want to use this, right? So again, knowledge of your identities helps a lot. Again, we're going to use that cosine squared and sine squared one. I just need to factor out a negative 1. If I factor out a negative 1, I again get sine squared, but now I get it plus cosine squared. And then again, since you know your identities, this is all equal to 1 right here, so I won't bother writing that anymore. It will just be negative 1 over sine squared x. And then similarly, 1 over sine squared x. Well, sine squared is really sine's reciprocal is cosecant. So it's negative cosecant squared x. And there's your derivative for cosecant. Okay, so I mean, as you kind of look through these ones here, I mean, you probably can fast forward if you want to the to this last slide here. I mean, really, what I'm doing right now is I'm just showing you all these rules, right? And what the showing you of the rules is important, but more importantly is you need to know how to use them. So we'll use them in a few examples in a second, because again, this is a pretty short lesson. Once I tell you the rules, there's not really a lot of background info to get to. This is kind of the meat of the calculus course right now, is trying to be able to derive basically anything. Polynomial, non-polynomial, square roots, fractions, exponents, logarithms, whatever. We need to be able to derive anything, right? So really, the trick then is, can you use these rules in context correctly? And I mean, it's challenging still. So, okay, anyways, let's try this one here. We're going to try the derivative of secant and cosecant. And like, you can already look on the slide and know what they're going to equal because they're already written there. But let's see that we can prove it. So if we want to write secant here, maybe here's another little trick. Rather than writing it as secant, let's write it as cosine of x to the minus 1. Because really, isn't that what a 1 over cosine is? 1 over cosine is to the negative 1. So then if I want to derive this, well, then we can do it like this. The derivative of that is going to be negative 1 cosine of x now to the negative 2. But then we need the derivative of the baby inside, and since the baby inside was cosine, its derivative, well, actually, let's wait a second here. Okay, so let's write that out, and then we'll write negative cosine to the negative 2x. And then the derivative of cosine is negative sine. Couple of negatives together cancel each other, so we can ignore the negatives. Cosine squared on the bottom, if it's a negative 2, cosine actually gets back to secant squared. And then you'll also have a sine squared. And so the derivative of secant is actually secant squared times sine squared. But that's not actually necessarily how we write it. That one works, but it's been written out a little bit differently sometimes. You know how secant can be, I mean, we already, right back here, we had 1 over cosine, right? Maybe, let me just go back and write it like this. You have 1 over cosine, but you have 2 of them, right? Because it's squared times by sine. And so sometimes what we'll do instead of this one, although this one is valid, the more traditional way is to combine this together and say, hey, isn't sine over cosine equal to tan? And then 1 over cosine right here is actually secant. And so there's our derivative. A standard textbook usually writes it as tan and secant multiplied by each other. And I mean, order doesn't really matter. It could be secant by 10. And I find this one very fascinating then, because the way this one works is that secant actually derives to itself times by a 10. So it actually stays the exact same as it was, only now you throw an extra tangent on, which is, I think that's pretty cool. So, okay, let's do the last one here. Let's try to do cosecant. So again, let's play that same sort of trick. Let's do sine x and then make it go to the -1. And then let's do the exact same derivative. So if you want to find the derivative of sine x to the -1, it'll be -1 sine -2x, right? Drop the exponent by 1. And then find the derivative of sine, which I'm just going to do in a second step. So you've got -1 over sine x, and then let's do another sine x. And then sine turns into cosine. And so one valid way of writing it would be, you could call this a negative cosecant squared, and you could times it by a cosine. And that works, but that's not the standard way of writing it. A standard way of writing it, they change it a little bit. I believe the reason they change it is because they don't want to have the squared sitting here. So even though that would work, you could write it more like this. You could have, like, say, -1 over sine x. And then you could take the cosine that was sitting over here and kind of bring the sine over there kind of next to it, so that you get cosine over sine, which is cotan of x. 1 over sine is cosecant of x, and you have a negative. And that's more or less the standard way of writing it, is it's cotan times cosecant, which again is interesting because cosecant then derives to a cosecant, but also with a cotan. So I think that's kind of weird the way it works. Here's how I memorize it. By the way, you don't need to memorize. It's not something you're going to have to do. But I found this really helped me. A secant is the one identity that doesn't have co in it. And so secant will actually end up being itself, but it'll have tan. Right? And tan also does not have co in its word. So secant does not have co in its word, and tan does not have co in its word, so it derives to itself with an extra one. Whereas over here, cosecant has the word co in it. Cosecant, right? Well, it derives to itself, but it also gets the tan function, but it gets the tan function that has co in its word, right? So cosecant goes with cotan, whereas secant goes with regular tan. No co's as part of them. So I don't know if that'll ever help you in terms of memorizing it for when you need to do that. So I won't make you guys memorize these. You'll get all of these on your final exam. But I'm fairly confident in saying that when you get to first year calc, you have to memorize all of these remaining rules. Your product rule, your quotient rule, your trig identities, your logarithms, your exponents. I mean, I knew some kids who they made flashcards to memorize all these rules. So knowing the rule is one part. The next most important part is, can you do something with it, right? So here's your 6. Sine, cosine, tan, cosecant, secant, cotan. Ideally, you will now know from those 6, you'll be able to know how to use them in solving something more complicated. So I've got, I think, 2 examples here. And we need to be able to do things like quotient rules and product rules and chain rules regardless. So let's give it a try. Right off the bat, this is one thing you can approach as a quotient rule. All right, you've got something divided by each other. But I have a different idea. I want to show you a little trick instead. Before I work with it, let's just rewrite it like this. 1 over tan, like that little bit there, the 1 over top of part, you could have written it with a -1, which means you may find it easier to take its derivative using the like drop down to power rule and use a chain rule inside. So you'd get -1, keep the baby inside, drop it down to a -2, and then times by your derivative of 1 plus tan x. And this is about the point in the course where I feel like this is why it's important to utilize Leibniz notation, because with Leibniz notation, when you start getting these things compounded on top of each other just over and over and over again, it sure helps to be able to, like, how do I want to phrase this? To be able to keep track of like what ends up actually needing to be derived and what doesn't need to be derived. Like it works better to keep track of this, because this 1 right here, if you want to derive this 1, it's 0. tan derives to secant squared, and maybe you can do this in your head, right? Like maybe that's an in your head sort of thing, but it's just, I think it's better just to keep track of it step by step by step. Be methodical. Don't make a mistake, right? So even if you can, I guess what I'm saying, long story short here, I'm getting off topic. If you can do that part right there in your head and derive it, that's awesome. But hopefully you'll agree with me, like as this gets more complicated, it's not worth it to do it like that, right? Like just do it in pieces, right? So anyways, this first step right here is just being left the exact same thing, right? You're not doing anything different. But then when you derive this, the derivative of 1 is 0, derivative of tan is secant squared. And so that is your final answer. You could write it as a negative secant squared x over 1 plus tan x all squared. That'd be kind of a nice way to clean it up. You could do some more simplifying if you wanted to, but again, to what extent is that helpful? That may not necessarily be all that useful. So, all right, let's try one more example here. Last one here. Let's try this guy. Now, this is probably the best example I can give you for why it's important to use Leibniz. Just because what we've got is a cosecant being cubed, and then there's still a baby inside. It's like this is really the epitome of there's everything happening here, right? Right. Maybe the best way of writing this is let's rearrange it first and call it 2. Then it's cosecant of 3x squared. And then all of that's to the power of 3. So we're going to need like multiple chain rules happening here. All right, so to find the derivative. Drop the 3 down in front, times it by the 2, gives you 6. Keep the baby inside. Cosecant of 3x squared. And now it drops down to a 2. Right? But this is where Leibniz is so important. Then do the derivative of the baby inside. And so your baby inside was cosecant of 3x squared. Okay, so keep writing stuff out. The derivative will be, I'm just going to modify this as I go along. Let's call this 6 cosecant squared of 3x squared. I'll just change that there. Okay, so then you need to know your derivative. Cosecant, what does it derive to? Well, it derives to a negative cosecant. Keep the baby inside. But it doesn't just derive to itself. Cosecant derives to cosecant and cotan. So this is really important to point out here, is that I also need to do a cotan, and the baby needs to stay inside of both x locations. So even though this is being multiplied by like a -1 there, this baby inside of 3x squared needs to be taken care of in both possible locations. And then that baby then needs to be derived to your 3x squared. It still needs to be derived as well. So, okay, so let's kind of keep working on this. This is all being multiplied, so I'm just going to clean it up while I'm going. Let's take this negative and times it by the 6 and make it -6. And then check this out. You have cosecant 3x squared right here, and you have cosecant squared 3x squared right there. So in a way, you're actually now back up to having 3 of them total. And then this cotan right here is a 3x squared. And then finally, you have to derive the 3x squared, which is 6x. And this would be a good place to leave it if you wanted to. Or maybe this would be the best way to do it. Maybe make it -36x. Cosecant cubed, well, all to the power of 3, and then cotan of that. There, either this one or this one should probably work as a derivative. Definitely not this one up here, right? This one's not ready yet because it still has a derivative left. So, in the first unit, and in the first like section on derivatives, I didn't ask you guys to do a lot of simplifying to make them look pretty. But you're going to discover when you're working with your cotans and your sines and your cosines everywhere, it really is beneficial to kind of do some work to try to make it aesthetically pleasing. Just because it's harder to interpret. Right? This is where math looks like funky mumbo jumbo, and you're like, what the heck are we doing here? So I would definitely recommend, like, even just this step right here, for those of you who are able to understand it, this step right here, look, you have cosecant squared of 3x squared, and you have another cosecant of 3x squared, and they're being multiplied by each other. This was a multiply sign right here. It was pretty ugly looking multiply sign, but it was chain rule, right? Which means that you have 2 of them multiplied by another one. It means you have 3 of them total, right? So, anyways, there's my lesson. It's a not overly long lesson, which is good because our next couple sections we have to spend a little bit of time talking about exponential and logarithmic functions. So those are maybe a little bit more challenging in terms of just some background info we need to talk about. But yeah, basically I've got 6 new rules for you to add to your list. So in a way, you should have known your power rule, your addition rule, your subtraction rule, your multiply rule, your divide rule, your chain rule, your implicit differentiation. Well, now you should be able to add to that 6 more rules of all of the 6 trig functions. And then in our next sets of notes, we will start talking about exponents and logs. So, okay, one last thought. I haven't been saying this as we go along because I've been motoring a little bit faster through some of these notes. Make sure you ask me questions as you get lost and as you're wondering what's happening. Make sure you ask questions. Make sure that you pause, rewind, you go over it again. But don't just leave it, right? Oh, and one more thought: don't procrastinate. Earlier in the course, many of you are doing such a poor job of being on top of things. Make sure that you get started on this right away. So this is our 3rd video. You should be able to then get started pretty quickly here on looking on your assignment and doing more videos. So, okay, we'll leave it there. Get a hold of me. Email me, VC. We'll chat with you guys later.